Well, I thought it would be a good idea if we started off this lecture with some magic. And every magician needs an assistant, so who's going to be the sorcerer's apprentice? You are? Right. You come forward. And your name is?
Sean.
Hello, Sean. Well, now look, this is an ordinary torch. You've all seen a torch. So we're going to start off by taking it to pieces. Let's take the top off, if it'll come off. Now you hold the battery, and I'll take the bulb out. I expect you've all done this, haven't you? Taken torches to pieces. And there we go. Unscrew the bulb. And let's just try and make sure we'll hold it across these. That's right, yes. See if it lights up. Yes, yes, everything's fine. Now, Sean, you put the battery in there, in that sort of magic box there, and I will screw the bulb into this holder. And I want you, Sean, to take this and put it on top of this perspex rod, you see. Now, we've purposely made it perspex so as you can see that there are no wires. Very important. There are no wires. Have a good look. No wires? Right. Now I'll come round here, and now for the magic. Watch this, Sean. I'm going to put my hand on the box here, and I'm going to say, light up. Go out. I'll try it once more. Light up. Go out. See if you can do it, Sean. Have a go. Hand on the box.
Light up.
No, you're probably not pressing hard enough on the box. Nice loud voice. Try it again.
Light up.
He's done it. Well, that's absolutely splendid. Thank you, Sean. Well, I think he learned to do that magic very quickly, don't you? By the way, I should perhaps say right at this stage that when you look at these monitors, you may at times find some funny patterns on them, and you may find some funny noises going on in the sound, because in this lecture we are sending some rather large ripples through the ether, and they're going to do some funny things. Now, I'm sure you didn't believe all that nonsense about my putting the hand on the box and all that, did you? You didn't fall for that, no. No, it was just another trick, wasn't it? Well, as a matter of fact, it wasn't entirely. It was really half trick and half magic. Mr. Coates, now Mr. Coates, you see, when I said light up, he was beaming electromagnetic waves through the door onto the bulb, and that was making it light up. And that was the trick. But, you see, electromagnetic energy, enough to light that bulb, was traveling through empty space, and that was the magic. Now, you see, I call that magic because magic is something that we can't fully explain. And in this lecture, I'm going to try to explain it. But I won't be able to because we can't fully explain it. But let's see how far we can get, shall we? Well, I've already talked about electromagnetic waves. So before we get on to those, let's have a look at some mechanical waves. What do I mean? Well, now, here's a simple one. I'm sure you've all done this. I'll take this rope. Very famous rope, this. I'll tell you about it later. Now, if I just give it a quick little jerk this end, that wave will travel up to the top. Do you see that? Fine. Well, that's not a very interesting one. We're all used to that, aren't we? I've got some more exciting ones over here, but I want some help with these. Who's going to help me? You are, that's right. You stand the other end there. Just first of all, we'll get the wave machine ready. This is called a wave machine. And there we go. You catch. Throw it back to me. Fine. Who'll catch it? Now, you caught that very well. See if you can catch a wave. I'm going to send you one. And I'm going to do it by giving this a flick now. Watch for the wave. There she goes. And you catch it. Jolly good. You caught it. What's he caught? Well, you see, not like the ball. He hasn't got something he can hold up and show us. But you saw it travel, and you saw him catch it. So something happened. You send me one. Lovely. Look at it, traveling along. Isn't that splendid? Now, nothing's really moved, has it, other than these things going up and down. Let's both send each other one. Do you think they'll bump in the middle if we do? Try one from both ends at once. I'll say 1, 2, 3, go. Oh. Now, you see, they passed right through each other. And this is a very important thing about waves. They didn't collide, really. It almost looked as if they hit each other and bounced back, but they didn't. They passed right through each other. And in fact, it's very important that waves don't interfere with each other, because if they did, we wouldn't be able to hear all the separate sounds we can and tune into all the radio stations. Very important thing about waves. Well, thank you very much indeed. That was very good. I'm just going to demonstrate one other thing. You sit down. I'm going to see if I can... Thank you. You deserve a hand, yes. I'm going to try a standing wave. Send one up to the end and make it interfere with itself on the way back. I don't know whether this will always work. I'm just going to be careful on this one. Now, do you see the waves are virtually stationary? All that's happening is these rods are all bouncing up and down. We call that a standing wave. We'll say more about that later. Well, that's a nice machine, isn't it? Fine. Well, I'm going to move on now to another sort of wave, one that you're all, I'm quite sure, used to. We'll uncover this. And this is a wave in water. If I can get it going, I think I'll use this one. If I sort of pump the water this end, we can gradually work it up, and you can see there's a wave traveling along the water. You're all used to that, I'm sure. But the difference is, of course, that the water is now sort of what we would call continuous. It isn't made up of a lot of bits and pieces. It's just a fluid, and it's behaving in just the same way. And I'm sure you know that although we can't see sound waves also are waves traveling through the air. I've got a little pipe here, I'll blow it. Does anyone know what note that was? Can they guess? What was it? A. Absolutely right. Some of you have got absolute pitch. Do you know how many vibrations a second? How many?
440.
440. Absolutely right. Very good. 440 vibrations a second going out in the air. We couldn't see them, but they were there. Well, I'm going to show you now a very famous experiment that was done by Professor John Tyndall in this very institution. This is the actual machine he used. I'll take the top off. Yes, you better take it off. Fine. Now, you see, this was a bell. This is the actual bell, incidentally, that Tyndall used. It's quite exciting, isn't it, that you can come to this institution and use the same pieces of apparatus. And there's a little hammer here, and if I just let it go for a moment, you'll see now, what he did, I think you all know, you may have seen this experiment, but I'm going to add another piece, you see. What he did was to put the top on and suck the air out and see if we could hear it. Now I've got another device here, this, and I'm going to add this. He didn't have this. I'll just put it that way round. That's it. We've got to be careful because it mustn't touch the sides of the jar. Put the jar on. Just before you put the jar on, we've heard the bell. I wonder if we can just hear this noise that this makes. This is making a noise, and this is the device that's going to hear the noise. That's the noise it's making. Fine, put the lid on. The bell too. Now in putting the glass jar over the top, it's going to quieten down the bell, of course. It insulates some of it, holds back some of the sound, but you can still hear the bell, and I think you can still hear that. Fine. Well now, Mr. Coates is going to suck the air out, and while he's doing it, it'll take just a few minutes. Let's just say a few more things about waves, and indeed Professor Tyndall. I was saying Professor Tyndall, you know, he became a professor in this Royal Institution in 1853, and he remained and went on to become an honorary professor until 1893. That was for 40 years when he died. I mentioned that rope just now. That was the very rope that Professor Tyndall used in his experiments on wave motion. As I'm talking, you may be aware of the fact that the bell is getting fainter and fainter. You see, all these other waves that we've seen all relied on a medium, didn't they, of one sort or another. We started off with a rope, and the rope could carry the wave. We then went on to the thing I call the wave machine, and that was springs and bars. And then we went on to the water, that was a medium. And then we went on to air, and what Professor Tyndall, you see, was showing and proving quite definitely that you needed the air in order to carry the sound of the bell. Now you can still see, if you look in these monitors, you can still see that hammer working away. I don't think you can hear the bell now. Or if you can, it's very, very faint. Very faint indeed. I think at this stage we can switch off the pump. Let's just now see if I can hear it with this device. We'll switch it on. Now you can still hear that noise, can't you? Right? Taking the air out has made no difference. So what that has shown us is that the sort of waves, you can hear the bell now, it's come back. Yes? Thank you very much. So we're not dealing with the sort of waves that require to travel through air. We're dealing with these electromagnetic waves, and you may have noticed when I started, I said that the waves travel through empty space. And you may have thought, oh, well, it isn't empty, the air's there. But in this case, you see, the space was empty. We sucked the air out, there was nothing there, and the electromagnetic waves still traveled through. Well, how do we explain this? Well, let's start with some simple mechanical things. Look, I'm sure you're all familiar with things that do this type of thing. Let's get them all in motion. Now look, they're all doing different things, aren't they? But if we stop and think, they're all doing it for the same reason. They're doing it because there's an argument going on between two forces. And I want to talk about these two forces. One of them is a spring force, like that, and the other one is what I'm going to call an inertial force, and we'll talk more about that. But let's first of all talk about the spring force. Now, you've all, I'm sure, seen... Thank you. Where are the catapults? Thank you. The argument that I was talking about, here we can repeat this on this device. This is very similar. You see, it's got a spring here and a weight in the middle, and we can do this. Now, I want some help with this one because I'm going to, in a minute, stick a felt pen in the middle. But before I do, yes, you come round here while we're explaining this. I'm going to turn this round the other way, then you'll be able to get your fingers there. Now, in a minute, I'm going to ask you to catch hold of this, but I want you to imagine that these two things can sort of talk to each other, you know, Alice in Wonderland fashion. Do you imagine we've pulled it out here, you see? And at this point, the mass here is saying, I'm quite happy, but the elastic, this one, is wanting to get back. Right? By the time we get back to the middle here, the weight is saying, well, I'd be quite happy to stay here. The elastic is saying, I'd be happy to stay here, I'm sorry, but the weight is already underway. Right? I think, first of all, yes, I'll do this in a moment. Just stay here for a moment. This is a sort of a spring, isn't it? You're all used to this sort of thing. Who's like Faraday? If I pull this back, you see, there's a force there, and that's the force I was talking about that was trying to pull this back. The force was pulling this back. Oh, I've broken it. I won't be able to fire anything at you. That's the elastic force. You come round the front here before we play with this, and I'm going to get you to try to, let's roll this out. It's very heavy. See if you can lift it. Don't strain yourself. Ooh, you can. Right, drop it down. It's very heavy, isn't it? Now, that's very heavy. We say it's very heavy. It weighs a lot. But it has another property. You get to the other end. I'm going to roll it to you. It's got what we call mass. Now, there's a big difference. We've got to be careful we don't confuse weight with mass. You know the men on the moon, they find that if they try to lift things or move about, nothing weighs as much. Do you know how much less things weigh on the moon? How much? 1/6, that's right. So if they tried to pick this up, they'd find it was only 1/6 of the weight. But they found, when they went there, that one of the things they forgot was that when they moved about, if they tried to change direction, their own mass, although their weight was only 1/6, they were just as massive as they were before, it tried to carry on in the same direction. Like this ball. You all know, I'm sure you know people who you have a dickens of a job of getting them out of bed in the morning. You at last manage to get them out of bed in the morning, and then they run around all day, and then you have a dickens of a job getting them back to bed in the evening. I can see there's some faces here that are very familiar with this phenomenon, and it's one that we can call inertia. When it's difficult to get something going, and once it's going, it doesn't want to stop. And that's like this ball, you see. I'm going to roll it to you. Now I've got to push it, and you stop it. Okay, you push it back to me. Now, if I didn't put my hand there to stop it, it would just go on rolling. In fact, if there wasn't any friction, if we were in empty space, it would go on and on and on forever. You see, the one thing that this mass doesn't like is changing its motion. It doesn't mind whether it's standing still there or moving at 10 miles an hour or 100 miles an hour. It just wants to go on doing what it's doing. So come back here now, Stephen, and we'll look at this thing. This, you see, was in the same position. The elastic wanted to get back. By the time it gets back, the elastic's happy, but the mass wants to go on doing what it's doing. It goes forward. And so we have this movement, this argument. The two things are never happy at the same time. Now I'm going to try to put a felt pen in here. And it's a bit difficult because it's just got to touch the board. With a bit of luck, we'll be able to make a graph and draw out what this thing is actually doing. So let's start this end. Now, if you've got strong fingers, right, can you hold that? Fine. Okay? And when I say go, you let go and I'll push this. Go. Fine. Now, it's drawn something. What would you say that was? What?
A wave pattern.
That's a wave pattern, isn't it? A very good description of it. A wave pattern, you see. In moving that along, we've now made a record of what that was doing with time. Thank you very much indeed. That's very useful. Thank you. If it took me 1 second to move this along from there to there, and we count up 1, 2, 3, 4, we could say it had done 4 oscillations in 1 second. This would be time, you see. So that tells us what's happened. And now we see, too, that each time it swung, it lost some of its energy because of friction, and it got smaller and smaller. So this is the sort of thing that happens. This is the argument that happens when you bring together these two forces, one that always wants to go on doing what it's doing, and another one that always wants to get back to where it was before, the elastic force and the inertial force. Now, you may say, what on earth is he telling us all this about, things that bob about and swing about when we're supposed to be talking about electromagnetic waves? Well, as a matter of fact, there's a very, very big connection, because you remember in the first lecture, the very first lecture, I was talking about two forces, the electric force and the magnetic force. And if you remember, one gave rise to the other. An electric force, when it was moving, produced a magnetic force, and a magnetic force produced an electric force. And I'm going to show you that really these two, the electric and the magnetic, were those two forces in disguise, or at least their behavior was exactly the same. Now, if I want to draw out one of these wave patterns that we just saw that's moving many thousands of times a second, I can't do it with a felt pen, and we use this sort of thing. I'm sure you've all seen these. This is a cathode ray tube. It's not the sort that you look at television pictures on at home. It's quite small, but it's the sort of thing that we can draw waveforms on. And I can show you how this works by, sorry, take that one off. Just watch. I'm going to bombard this powder on the front of the faceplate with light. I'll just do a quick sort of like that. Now you can see it's sort of drawn across on the front. The sort of thing that we're going to be drawing on the front is a squiggle like that, isn't it? But of course that was quite slow. What the light did there was to bombard the phosphor and cause it to glow. That's a property. But in fact, we don't do it with light. We do it with an electron beam, which is much more convenient, and we can focus it into a very fine beam. The beam is generated here. It travels up the tube very fast, is focused to form a very fine spot, and we can deflect the beam horizontally from left to right or right to left and vertically, and we can use this to draw out those patterns just as we did by moving the board, only at a very much faster rate, you see. Well, I expect you've seen these before, but it's worth just stopping to think how this is happening, because it can draw patterns at an enormously high speed. So this is the sort of thing we're going to use. Cathode ray tube. I want to come now to show you how it is I'm able to say that the two forces we talked about, the electromagnetic, are really like these two mechanical forces. Now, do you remember in the first lecture I talked about a Leyden jar, and we saw how we could charge a Leyden jar? We actually charged it with a great big Wimshurst machine. Well, nowadays we don't use Leyden jars. the Leyden jar would store electricity. Well, one of these little things called a capacitor will do the same thing, and this will store electricity. And this box here is simply a box which is generating a high voltage, and if I put this across the terminals, I will charge it with electricity. And now it's like the catapult, you see. It's already, the force is already there, it's waiting to go back. And if I take the screwdriver, we've discharged it. Is that clear? Everyone hear the crack? So that's very much like the capacitor, like the spring, you see. It's all charged, ready to go. Now this is a coil of wire, and this is the other part of the story. And this is the thing that behaves as if it has inertia, and I'll tell you why. You remember in the first lecture, when we put current through a wire, as Ørsted did, it produced a magnetic field. And you may remember too that when Faraday realized this, he thought the reverse would happen. He was right, that if you moved a magnetic field in front of a wire, it would produce a current. Well, if you try to push current through a coil of wire like this, you produce a magnetic field, but the magnetic field in turn produces a current, and the current opposes the one you're trying to push through the wire, and so you have exactly the same sort of reaction that we had when we tried to push that heavy ball. You see, it wants to go on doing what it's doing. It doesn't mind, once it's climbed up, it's happy to pass a steady current, but it doesn't want to change from one value to the other. So this is the one that is behaving as if it had inertia, and this is the one that's behaving like a spring. And if we join the two together, they're going to have the same argument as the argument that our mass and our spring did. Here, in fact, we have them rigged up, you see. I've joined them together, so now they're going to argue with each other. There's the coil, and there's the capacitor. When I throw the switch, we're going to repeatedly charge the capacitor and let it discharge through the coil. And on this oscilloscope, we'll see what happens. You see, that pattern is very similar to the one we had with the spring and the weight. In fact, it's taking 1 millisecond, 1,000th of a second, to go across the screen. It's quite fast. And the reason you see it flashing is because it's just repeating itself 4 or 5 times a second so that we can see the image. So you see that is behaving in a very similar way to the mass and the spring. In fact, if you can visualize it, the electrons are racing around the coil, swinging in, recharging the capacity is discharging back into the coil, and here we have this damped oscillation. So you see there is a connection between these mechanical oscillations and the electrical. It was Heaviside who realized this. Not Heaviside, I'm sorry. It was Clerk Maxwell who realized this in 1864, Clerk Maxwell. This was one of the most brilliant pieces of mathematical work that anyone's ever done, because just knowing the work of Ørsted and Faraday, he was able to calculate on paper, just using a pencil and paper, that electromagnetic waves would be produced and go through the ether if you moved an electric charge. He calculated this, and not only did he calculate it would happen, but he was able to show that the speed of the waves would be the same as the velocity of light. Now, this happened in 1864 that he published this work, and it wasn't until 24 years later that it was proved by a man called Hertz. And we use his name, Hertz. Instead of saying cycles per second nowadays, we could talk about the vibrations as being so many hertz in remembrance of his name. He was the one that first produced electromagnetic waves that traveled across empty space. And he'd used it with a device, he produced them with a device like this. This is very similar, you know, to Hertz's original transmitter. I'm going to swing it round first. You'll be able to see here It's got a big coil. There's a key here. When I press the key, it will operate this little buzzer here, which will keep on putting pulses into the coil. And just as we described it over there, the current will build up in the coil. It will get discharged across this capacitor. You'll actually see sparks occurring here, in this case, sparks across these two balls. And he connected these two large plates here to act as a radiator. He felt that these plates would not only act as a capacitor, that would act as a radiator and help to launch these waves into the air. And this is the sort of thing he used. Well, in a moment, I'm going to press the key, and you'll be able to see, get it right position. I want you to notice two things. When I press the key, first of all, we're going to see sparks across there. And those horizontal rods there represent the receiver. When I press the key, I want you to look at the little bulb in the middle, and we'll see what happens. Now, I'll press the key. Ah, not switched on. You see, it's lit up. But I've stopped pressing the key. We're not radiating anything, and it's going on lighting. Now, one of you young ladies come in the front. Just give that little bulb a tap, would you? Just that little rod in the middle. That's it. That's gone out. Now, I'm going to do it again, quickly. Give it another tap. Now, imagine I'm sending you a message, and each time I press it, you've got to tap it. Well, you see, what's happening is this. Thank you very much. This time, the bulb wasn't being lit directly from the electromagnetic waves. It was being lit from this battery. But what happened was when we radiated the waves, they were picked up by these rods and applied to the end of this little tube here. And the little tube is full of little metal filings. And the presence of the electromagnetic waves caused the filings to all stick together. They adhered. It was called a coherer for that reason. They stuck together, cohered. And once they had cohered, it was easy for the current to pass through and light the lamp. But the trouble was, you see, that once that had happened, we stopped radiating. They didn't decohere. They didn't unstick themselves. They just went on. And that is why the young lady had to tap it each time. So in order to send a message out on this sort of device, what they had to do was to arrange for a little buzzer to be operating as each time the light came alight. They wouldn't use a light, in fact. They'd use something you could hear like a buzzer. But another little tapper would be tapping away at this thing so that all the time it was freeing those little particles. Now, that was the earliest way in which electric waves were received. Hertz did it over a short distance of not more than about, I think it was 10 meters across the laboratory, first of all. I think it's only fair for us to have a look at the early transmitter. No? Yes. No. There's one thing, you're absolutely right. You see, Mr. Coates is here to help me, and it's very valuable having him here because just for the moment, there's one thing I meant to show you and I haven't shown you, and that is this very important fact of tuning. You know how you go up to a radio receiver and you turn the knob and you tune it, and you tune into the station you want. Well, again, there's a very good mechanical analogy of tuning, and it's this, that these rods, you see, again, we're back to springs and masses. Look what happens. If I cause this one to vibrate, this one will vibrate, and these two take very little notice at all. And that's because they're both what we would say tuned to the same frequency, or they both will resonate at the same frequency. Right. Now, if I wanted to retune this, if this was the receiver, to pick up this one, I'd have to shorten it to make it the same length, do it quite accurately. And now it corresponds with that one, you see. These two relatively still, this one vibrating once I cause that one to vibrate. And again, as you can imagine, I can lower it down still further. And you can guess the answer before I start. If I do that, this is going to vibrate because they're tuned to the same frequency. Well, once you've appreciated that these electrical oscillations are bouncing around just like the mechanical ones, you can see that we can do precisely the same thing. And when we tune into a radio wave, we're altering the size of our coil and our capacity so that it corresponds with those that are generating the wave, and that's how we pick it up selectively. Now, I think it is only fair at this stage to go back. You know, we had this hidden behind the door, and this was the transmitter that we started off with. It isn't like Hertz's transmitter. It's a small transmitter developing quite a bit of power, but at the moment I've just got a little coil across here. And if we switch it on, here's a little detector. Again, I'm using a bulb. We'll see that as I bring the bulb up near the coil, whoa, lovely. See, there's plenty of power there, but I have to hold the bulb quite near to this coil because very little energy is being radiated. And that's the situation that we had when we were just sending the current oscillating backwards and forwards just now, and you saw that wave, you see. But suppose now if we just switch off for a moment, I will untie one end of this and pull the coil out, and now notice that it only is connected one end. This end is free. I wonder if you can guess what's going to happen when we switch on. The electrons are going to be rushing up and down this wire, and this will cause now not the energy to be confined at all. It'll now be radiated, and we can prove it by taking this as our detector, not a little coil this time. And now if I hold this up, you see there's plenty of radiation occurring here. I can walk around, still quite strong, all the way around. And in fact, wherever I go around this wire, you will see that it's capable of lighting the bulb. If I get too far away, of course, it fades away. So we have this energy being radiated, as bright, from that aerial, and it's exciting current in this, traveling through empty space, as I said. If I put it horizontal like this, there's very little at all. In fact, I can come quite close and get nothing. If I get too close, we do get something. But that's because these waves are going up and down that way, and the receiver's responding to waves as it were going that way. This we'd call vertically polarized, and so we have to put our aerial that way to get the effect. So there is a typical sort of transmitter, and this is the sort of thing that you're probably used to seeing on our roofs, picking up radio signals. Thank you very much. One of the things that Hertz proved was not only that radio waves could be produced in what they then called the ether, and we still call it the ether. We've got to call it something, although in fact there's nothing there, but what can you call it? He found that, but he also was able to demonstrate that they did behave in many ways like light waves. And I'm going to use this apparatus now to show you the sort of thing that Hertz was able to prove. This, in fact, I'll just explain the apparatus. Underneath is the power supply and the transmitter, which is generating the electromagnetic waves. And the waves are coming up through a cable. They're being launched in here, and they're running along this little pipe here called a waveguide, and they're coming out of this little horn here. Now, these are very small waves. The wavelength, which I spoke about, the wavelength is less than 1 centimeter. If we take our long wave transmitter, the long wave ones, the longest waves we transmit in this country, they're 1,500 meters, and as you know, that's roughly a mile. So we have this enormous range, you see. The big ones are a mile long, and these ones are a little less than a centimeter, and that's why they'll travel down this little tube, and they can be launched through this little horn. And I can pick them up with this, using this as a receiver, and again, watch the light bulb. And if I get it in the right position here, you see it's picking up these waves being launched in the space in between. Even my hand, you see, will interrupt them. Now, what Hertz was able to show was that if you put an obstruction in, for example, metal, you got nothing at all. And I can wave this about. No, absolutely nothing. Pick it up again. This is quite a concentrated beam coming out of this little horn, you see. If I raise this, it soon goes dim. And if I pull it, it doesn't rock it. There's saturating a bit. That's right. So I've got to hold it in the right position. Now if we hold up a piece of wood, well, this has some effect. Not a lot, but it certainly has some effect. If I hold up some wax, it's quite transparent. It has virtually no effect at all, the wax. There's another thing we can show, and that's reflection. If I go back to this metal one again, seems to be rather a lot of it about from here. More than I expected.
I think it's still correct thing.
Is it? Yes. Never mind. It's still... We'll put this on. Now behind it, of course, I get... No, it is picking up from somewhere else. The thing about experiments is, of course, they're always good ones if they go wrong in places, because that proves that they are genuine experiments, you see. If they don't, they're rigged. Now, this one's genuine, you see, because it was not behaving as it should have done. Now, if this is reflecting, the wave ought to be hitting this metal plate and coming off here somewhere, and here it is. And as I turn the reflector around, you'll see, I hope, quite clearly that that is reflecting. Now, we'll just try one more of these things. You all know a glass prism will bend a beam of light. Well, this isn't a glass prism, it's a wax prism. But as you saw just now, the waves travel through the wax, these waves, these centimeter waves, just as if the wax was transparent. What I didn't tell you was that the wax does have some effect. It slows down the waves, it slows down the velocity of the waves, so they don't travel so fast. So if you imagine the wave entering this prism, the bit of the wave that's going this side hasn't got so much wax to travel through, so it will be slowed down for a short time, whereas the wave traveling at the back here will be slowed down for a longer period of time. So you can imagine this bit is going to be slowed down, and now it'll be slowed down, and it'll bend the wave round because this will drag behind, and we should be able to pick up the, if we can just get the thing in the right position. Here we are. Now, as I rotate the prism, you will see there it is. The maximum is there, where the wave is going in there and being bent and coming out there. So it is behaving very much like light, except that different materials are behaving in a different way. In this case, wax is behaving like a clear object. Thank you. Well, now, those were centimeter waves. If we go on making waves shorter and shorter and shorter, in the end, we come down to waves that become visible. You're all familiar, I'm sure, with laser beams. You've heard a lot about laser beams, and laser beams are electromagnetic waves. The right way to look at it is not that the laser beam itself sort of lights up, but it is that the waves are short enough to come within the range of waves that our eyes respond to. You see, our eyes respond to a narrow range of frequencies, of waves, and the laser beam comes within that range. Now, if our eyes were very, very big, and they're not, we could see maybe longer wavelengths. We could see radio waves coming out of the transmitting aerials from our broadcasting stations. But as it so happens, our eyes aren't all that big, and so they can't see them until they're very, very small indeed. But the eyes respond to these minute waves, and the laser beam is an example, as is any light, of an electromagnetic wave where the wave length is so short that our eyes respond to it. And I have a laser beam here, which I'll switch off for the moment, and just line this up. And I want you to see something which is rather important. Switch it on. Now, can you see the beam this is the laser itself. The beam is traveling straight through the laser. I have it tilted at this angle, and it's landing up on the paper just there. You can all see that. You can probably see that on the monitors, the little bright spot. In this little tank here, I've got some fluid, and it happens to be a mixture of glycerine and water. And the glycerine is heavy, and it's tending to lie at the bottom, and the water is on top. Don't take any notice of this little bit of clouding that's occurred. That's not part of it. The point is that the wave is going to travel more slowly through the glycerine, just as the wave we saw traveled more slowly through the wax than it does through the water. And so the bottom end of the wave is going to be traveling more slowly than the top, which will cause the wave to bend. Let's see if this happens. I hope it does. I'll keep my fingers crossed. The solution should be all right. I'll move it over. Yes. Now, do you see that? It's bent the beam, and it's now arriving right down here. You see that? Fine. Was there. It's come down to there. That effect is a very important effect indeed, because it accounts for something that puzzled the scientists a great deal. When Marconi, in 1901, following Hertz's demonstration, finally, he was the experimenter, he was the one that went ahead and said, let's try it. And everybody thought, well, waves aren't going to travel around the Earth, they're going off in straight lines. But Marconi managed to transmit signals across the Atlantic. And then the scientists started to argue with each other as to why this could happen. And some of them said, well, maybe it's because they're clinging to the surface of the Earth, and they did some more sums, and they found that they would cling to a certain extent, but this wouldn't be enough to account for the fact they could go all the way around and across the Atlantic. Two men, Kennelly in America and Heaviside in this country, both had a thought, just about the same time, that if there was some layer high up in the air that was acting like a reflector, maybe the waves were going up and getting reflected and coming down again. They didn't quite know the mechanism, but this was the only way that they could see that we could explain this phenomenon. And then later on, people like Sir Edward Appleton worked this out, and they came to the conclusion this was absolutely right, and they did some experiments to prove it. And I'm now going to show you a demonstration of how this actually happens. Now, I did talk about the thought of there being a reflector there. We think of a mirror as being a reflector, something that literally does reflect. But as you've seen here, you don't really require a mirror. You can have a medium which is, I'm going to say optically, but when I say optically, I mean to radio frequencies as well. If it is less dense at the top than it is at the bottom, then the wave will be bent and it will act like a mirror. Now, this is a demonstration to show, before we turn the lights down, and I'll need to do this, the idea of this is to show how this comes about. Now, you see this, first of all, this band along here. This represents the curvature of the Earth. You see, that's part of the Earth's surface. And this represents one of the layers in the ionosphere, which I'll talk about, and this one is another layer. Now, the way that these layers arrive and what they are is quite complicated, but it does depend on there being some atmosphere. What's happening is this, that the sun's rays, and during the daytime, whether the sun's shining on us or not, we may have some clouds, you see, the sun's still there, it's traveling through the outer atmosphere, and the ultraviolet part of the sun's rays, these are high energy parts of the sun's rays, are managing to dislodge electrons from the little gas, the atoms which make up the gas of the atmosphere. And once the electrons are dislodged, you've got a charged layer. If these can all get together, they're a charged layer. But in the daytime, lower down, they very quickly hop back again because the gas molecules are quite close to each other, so they're hopping away and hopping back again. There's an awful lot of activity going on. And in fact, in the daytime, these radio waves that we transmit get absorbed. I'm now talking, first of all, about the longer wavelengths. They get absorbed, and we hope to see this. But when night falls, this absorption layer, like a cloud below the reflecting layer, disappears, and now they go up to the reflecting layer and get reflected. And this is the thing that causes trouble when we try to receive at night, particularly distant stations sharing the same wavelength, and also our own stations at distances interfere with each other, and we'll try to see this effect too. Now, this higher layer is one that is still higher, roughly, just to give you an idea of scale. This first one is about 100 meters or so from the Earth's surface, and this one is about 300, but they're not rigorous heights. They float around quite a bit. There's one still higher. Depending upon the frequency or the wavelength, whichever way you like to look at it, these layers will either let some waves through or not. Some of the waves go through one, some of the waves go through the other, and this is what I want to demonstrate. So I'm going to get them to put out the lights, and I'll switch on the... Fine. Now that's the situation that exists at the start. I'll put on this torch. Perhaps somebody could just come slide the thing for me when I want it. Now you can see the arrow. I'll just get this in the right position first. First of all, you can see the ground wave. This is illuminated, and it's traveling along the ground, and that's lit up, and it's beginning to fade because the further the wave travels, the weaker it gets along the ground, energy gets lost, and by the time we're out here, you see it's quite faint. Well, now some of it is going up to this absorbing layer. You've got to imagine that this is the transmitter right down here, and some of it is going up to this absorbing layer, and the layer is absorbing it. That's what happens in the daytime. Now, when night falls, the absorbing layer disappears. Thank you, Mr. Coates. And now you see the waves are going up to this first layer, called the E layer, and down they're coming, and would be received quite strongly, you see, here, for example. That's if they went up at this angle. And they could be interfering with the waves that were traveling along the ground, because this path is a longer path than that path, and so the two waves aren't arriving at the same time. And as you can imagine, that they then interfere with each other. So that's what's happening to the very long waves and the medium waves. Now, if we go on up to the... That incidentally, you see, is a nuisance, because it does mean to say that even at quite long distances, transmitters using the same frequency will interfere with each other on medium waves. Now, if we go on to the shorter waves, onto the green, the green light, incidentally, the wavelengths we're using we did start off with a long wavelength light, and now we're going on to a shorter wavelength light. Now, these are the ones we use for our frequency modulation, our FM sound service at VHF. You've probably heard about this. And also, so sorry, I'm one behind. These are the short waves that we use to transmit overseas. These are the waves that caused Marconi's signals to travel across the Atlantic. And these waves can travel up to this higher layer. They travel through the first one and get reflected. And you see that they come down at a much further distance away, starting here, traveling right through the first layer, coming down, and they can travel long distances. And furthermore, they can get reflected up again and come down again and do several hops. In fact, they can go right round the world. These are the short waves that we use for sending overseas signals, such as our overseas broadcasting services. This is a good thing, you see. First of all, it's a nuisance, now it's a blessing. It's worth mentioning at this stage that they rely on an atmosphere. This effect, the ionosphere, the reflection, relies on there being an atmosphere. And indeed, on the moon, you couldn't send a signal round from the back to the front. No atmosphere. And you may have noticed that when the astronauts get round to the back, it goes into a radio silence for this very reason. If we move on to the ultra-high frequencies, and these are blue, shorter wavelengths still, you see now these are traveling right through the first layer, through the second layer, and that's just to show you they've arrived there, but they're going off into empty space, as it were. So for these frequencies, and these are the UHF frequencies that we use for UHF television, it's no good sending them up like that. They have to be sent radiating along the surface of the Earth, and they travel very much like light waves. The shorter the wavelength, the more do the waves travel and behave like light waves, and that's why the UHF waves travel more or less in a straight line, can be obstructed by objects. Now, this is a model of a typical sort of aerial system, a mast, that's been loaned to me by a firm who makes these things, BICC. And I merely thought it interesting to show you. You've probably seen these things dotted about the country at odd places. This particular one is the sort of thing that's used for a relay station. But I think it'll help me explain two things. It isn't used for long and medium waves, but if we wanted to radiate long and medium waves, what we'd do is we'd take a mast like this, a tall mast, and we'd feed the electromagnetic energy into the bottom and send the electric charge racing up and down the tall mast from the ground, and this would be sending out the waves, a tall mast, long or medium waves, fairly long wavelengths, you see, a mast of comparable size, if possible, with the wavelength. But when we come to these, that's because we want them, of course, to hug the ground, you see. We're sending them straight from the mast like that. When we come to the short waves I mentioned, and the UHF waves in particular, as used for television, well, what we want here to do is to have a tall mast still to get them well up in the air, clear of the ground. But you've seen these dipole things, two wires like that. Well, this cylinder here, that's a weather protection, will have an array of these inside arranged so that it transmits rather like a searchlight will send a beam of light out in all directions. So the radiation is taking place from the mast. It's carried up there by a feeder, and it radiates from the top. These things, by the way, are just dishes for other communication purposes. I thought it just useful to show you that, just to get an idea how the actual waves are launched, because I know you've seen these things. Well, in this lecture, what I've tried to explain, and indeed it's very difficult because I said it was magic, is how it is we're able to send electromagnetic energy through empty space. We don't really understand it fully, but you can see that once we have those two things that Ørsted and Faraday discovered, that electricity would produce magnetism, magnetism would produce electricity, you have a sort of an Ørsted-Faraday, Ørsted-Faraday, Ørsted-Faraday leapfrog game going along through empty space. So far, we've merely shown that you can interrupt such a wave and send out Morse signals. But in the next lecture, I'm going to be discussing what we have to do in order to send out sound and music, the sort of thing that we've come to know as sound broadcasting. Thank you.